Burn like a pro.
Have you ever looked at a chemical formula and just thought, wow, that looks like a secret code? You know, all those letters and numbers, they can seem pretty intimidating. But what if I told you they actually follow a really simple, logical set of rules? Well, in this explainer, we're going to crack that code together. Okay, let's just jump right in with a classic chemical mystery. You see something like Fe2O3. Now, we know the letters stand for elements, right? Iron and oxygen. But what about those little numbers? What do they mean? And how do we go from this code to a name we can actually say out loud? Well, it turns out it doesn't matter if you're looking at something simple like NAF or something you see every day like CO2. The whole translation process always kicks off with one single, incredibly powerful question. If you get this question right, you are already halfway home. So what is this master key? Let's get right into it. It all boils down to one fundamental question. This is the first filter, the starting point for every single compound you're ever going to see. See, before you can name anything, you've got to know your ingredients. Every single element on the periodic table falls into one of two big categories. It's either a metal or it's a nonmetal. And just like grammar in a language, that combination is what tells you which set of rules you need to follow. And here it is, the decision tree in action. It all starts with that one question. Is the first element a metal? If the answer is yes, you go down the ionic pathway. If it's no, you go down the covalent pathway. It's that simple. Two totally distinct paths, each with its own rulebook. So let's explore that first path, the ionic pathway. This is the one we take for any compound that starts with a metal. You know, the basic rule here is actually wonderfully simple. The first element, the metal, it just keeps its name. Calcium is, well, it's just calcium. But the second element, the nonmetal, it gets a little makeover. We just swap out its ending for the suffix "ide." So chlorine becomes chloride. Put them together and you get calcium chloride. See? Easy, right? Now, that simple system works perfectly for a lot of metals. But of course, there's always a catch, isn't there? It hits a bit of a snag when we run into a special class of metals that are, let's say, a little less predictable. And this brings us to a special group called transition metals. See, elements like iron can form different types of bonds with different charges. So to avoid any mix-ups between, say, FeO and Fe2O3, we use a little precision marker, a Roman numeral right in the name that tells us the metal's exact charge. That's how we get iron 2 oxide versus iron 3 oxide. Zero ambiguity. All right, let's rewind and go back to that fork in the road, our decision tree. This time, we're taking the other path. This is for when our first element is not a metal, which means the whole compound is made of only nonmetals. Now, for these guys, the covalent compounds, the naming game is totally different. We can't rely on charges anymore, so we have to be way more explicit. We use these prefixes to literally count the number of atoms of each element. So mono is 1, di is 2, tri is 3, and you get the idea. And this is why those little prefixes are so absolutely crucial. Just look at CO versus CO2. They're both made of carbon and oxygen, sure, but they are worlds apart as substances. CO is carbon monoxide, 1 oxygen. CO2 is carbon dioxide, 2 oxygens. That one little prefix tells you literally everything you need to know. Okay, so we've got our two main highways down. But, you know, just like any language, chemistry has its quirks, its special cases, and a few exceptions that are really good to know. First up, polyatomic ions. Honestly, the best way to think about these is as little pre-assembled chemical teams. They're groups of atoms, like sulfate or carbonate, that are all bound together, and they act like a single unit with its own special name and its own charge. And because these groups act like one unbreakable team, they get to keep their special team name. So when potassium links up with the sulfate group, we don't change the ending to "ide" or anything. It's just potassium sulfate. The team name stays intact. And finally, we've got a few celebrities in the chemical world. I'm talking about compounds like H2O and NH3. They were found and named ages ago, long before we came up with all these systematic rules. So out of tradition, they just get to keep their famous names, water and ammonia. They're way too famous to be renamed. So let's put it all together. Let's try one. How about MgCl2? Okay, first question. Is magnesium a metal? Yep. Is it a transition metal that needs one of those Roman numerals? Nope. So it's just magnesium chloride. Simple. Now, what about SO2? Is sulfur a metal?
No. So we need our prefixes. That gives us sulfur dioxide. You see how that logic just flows?
And here it is, everything we've talked about all in one place, the master matrix. This is your cheat sheet, your complete summary of the 2 chemical languages you can now read. On one side, you've got the ionic rules, all based on balancing charges, and on the other, the covalent rules, all about counting atoms with prefixes. It's your complete diagnostic tool. So, what does this all mean? It means you now have the key. You can translate chemical formulas. And this isn't about just memorizing a bunch of rules. It's about actually understanding the fundamental grammar of how our world is built. You can now read the ingredients list of the entire universe. So the only question is, what are you going to unlock next?